Hi, everybody, and welcome to the Fast Code Seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy. I co-chair the organizing committee for the Fast Code Seminar, and I lead the community outreach for the larger Fast Code project of which the seminar is a part. Before Yihan introduces our speaker, I'd like to take a minute to let you know about the Fast Code Seminar and the larger Fast Code project. The front page for the Fast Code project and community is the website fastcode.org. I put the link into the chat. I'm sharing my screen so you can hopefully see the Fast Code site. It's an open source community dedicated to advancing software performance engineering. And this website gives you kind of places to see the highlights of what's happening in the community, whether you're researching, teaching, or learning, practicing, trying to get involved. We would love to have your input. Here you can see the Fast Code seminar, including the schedule of today's talk on compressed data structures. I want to let everybody know we have an exciting speakers lined up for the next few weeks. Mosharat Chowdhury is going to be speaking in May on energy optimal AI, which is a different take on software performance engineering than we often have here. So I encourage you to check that out. Laxman Dhulipala is scheduled to talk a few weeks after that. When you look at Peter's talk here, Engineering Compressed Data Structures, the web page on our site for his talk, we have posted the slides. So I think Peter thought it would be handy for everybody to have access to that. So you can get that by going to his talk and clicking to get your copy of the slides. We are recording so you can see the video as well. The only other thing I wanted to mention before I turn it over to Yihan and Peter is that this, of course, is not just a seminar, but it's part of a community. At our last seminar, which was by Jan Vassenberg on highway, someone said, hey, wouldn't it be great to have easier ways to get into SIMD and highway? And so a team has formed that is creating a tutorial for highway as we speak. They've gone through a few meetings. And so I just wanted to let everybody know that if you feel inspired, like anything that comes up in one of these discussions would be an opportunity for something to happen after the discussion, please speak up. So use the chat. I'll be monitoring and asking Peter questions as they arise. And that's all I have to say. I'm going to turn it over to Yihan to introduce our speaker.
Okay. Welcome everyone. Today our speaker is Peter Sanders. He's a professor at the Castro Institute of Technology, and he now leads the algorithm engineering group at the informatics department of KIT, in the Institute for Theoretical Computer Science. Peter has won a number of prizes, has designed a lot of algorithms covering all areas or all kinds of algorithms, data structures you can think about include sorting, SAT solving, data structures, graph algorithms, communication scheduling, uh, and so on. And many of them involves parallelism or different memory hierarchies. So today he will be talking about engineering compressed data structures. So let's welcome our speaker.
Yeah, thank you, Johan. So I guess that's my cue to share the screen.
Looks
So can
good.
everybody see the screen?
Yes.
Great. Then I go to full screen mode. Um, so, okay. You have this full screen now?
Full screen.
Yeah.
Great. So anything else we have to do before I start?
You're good.
Okay, so thank you for inviting me to give a talk at the FastCode seminar. As far as I see, I'm a little bit more on the theory and design part than previous FastCode talks, but I will try to make this bridge to performance engineering whenever possible, and maybe explain why having this wider view is also useful. So I will first do this motivation I just mentioned, and then I will talk most of the time about different variants of hash tables, with a particular deep dive on specialized variants, in particular perfect hashing, also explaining why that can be useful. And then if there's more time, I will talk about another specialized hash table, namely static function retrieval, and a little bit on approximate membership query filters, which are also known as Bloom filters. And if there's even more time, there will be a little bit on bit vectors supporting rank and select operations in constant time, which is kind of a building block for a lot of compressed data structures also. So why is this a fast code talk? The compressed data structures I'm talking about have a dual purpose here. On the one hand, you can use them in performance engineering of many applications. Particular databases, I would guess, but probably also others. And on the other hand, what I present here technically are maybe interesting case studies in algorithm engineering and performance engineering, and maybe some of these techniques can transfer to very different projects also. So this is all part of the methodology of algorithm engineering that takes a kind of holistic view on algorithms research, where we are modeling our problems, designing algorithms, analyze them formally, implement them, and evaluate experimentally. And that's kind of a cycle that you probably traverse multiple times before you have solutions you like. And that also gives you a tight coupling to applications. And one of the high-level goals of this is to bring theory and practice together, and that's something that moves me very much in my research. And I think that's something useful for both theorists and practitioners. Because for a practitioner, having theoretical results gives you additional robustness of your solutions. The theoretical view leads often to better algorithms, and in particular, the theory guides the tuning. But also, I think theorists should care more about the practical side of what they are doing, because at the end of the day, you want to be relevant, right? And there are too many areas where there's a lot of theoretical research that's basically ignored, and very often because practical issues are not considered enough. But it also helps you to find the right models and questions. For example, you could look at also looking in analyzing constant factors and then not just asymptotics, or using more refined models of your inputs like smoothed analysis, etc. Particularly in this talk, a recurring theme will be that we have, from the theoretical point of view, lower bounds on the space, and maybe some quite theoretical solutions that achieve these lower bounds, but they seem out of reach for really practical solutions. And at the end, we are actually getting there that both things fit very well together. More particular motivation, why is it interesting to look at compressed data structures? So we have here this general trade-off between space, construction time, and query time in the context of static data structures. That's what I'm talking about today. And space is kind of important due to several reasons. Very often, it's actually also making your algorithm faster to be space efficient, because if you fit your data structure in cache, or most of it, then your algorithm will run faster. Nowadays, with the memory crisis, I don't have to tell anybody that the money you pay for memory is very expensive. and indirectly also it's something about energy consumption of all of this. The concrete applications of the things I'm talking about here are, at least traditionally, in databases, in bioinformatics, but also in search engines, or when you do brute force search for kind of combinatorial optimization. And I guess even machine learning has a couple of applications for these things. Yes. So a high-level view on what you will see in the examples below may be that we have a kind of design pattern for algorithms where if you look at this diagram between space and speed, your starting point may be somewhere here, taking quite a lot of space, being reasonably fast. And we will make a kind of trajectory where we are first looking at getting more and more space efficient, not so much caring about speed. Then we arrive here with something that is almost achieves the lower bound in space. And then we have understood the problem so well that then we can get much faster with performance engineering and start to fan out a spectrum of solutions that have different trade-offs between speed and space. And what you end up is a set of configurations that are much better than what you had before, actually, both with respect to space and speed. So that's what we are going to see here in multiple examples. So let's get more concrete. So what do I mean with hash table variants? So you all know, I assume, vanilla hash tables, which are maybe one of the most frequently used non-trivial data structure, which have a rich set of operations that are all supported in expected constant time, inserting elements, deleting elements, querying elements, maybe retrieving or updating associated information. So here you would, for example, have an array storing the characters of the word algorithm in a kind of linear probing data structure. But this is not the ultimate thing you can do. Regarding space, you store keys, associated information, empty cells, or maybe also pointers, which gives you quite some overhead compared to the optimum thing you could think of. It's also not optimal locality, which can be a bottleneck. So if you look at this from the point of view of low bounds, a general hash table storing n elements with u-bit keys and r-bits of associated information basically takes u plus r bits for each element. Maybe if you look at succinct hash tables, it's minus log n, but that makes things more complicated and there's some additional overhead. The special case where you have a static function evaluation, you can only retrieve the associated information. But then, surprisingly, it turns out it's enough to just have r bits of storage for your associated information. And there are solutions that do that without much additional space. And of course, that's also an obvious space lower bound. Another specialized thing is an approximate membership query filter, where you only have the membership query and you additionally accept some false positive probability. So you may get the wrong answer with probability f, and then there's a lower bound of log 1 over f. And we will see that also that can be achieved in practice. And finally, for perfect hashing, you injectively map your keys to numbers from 1 to n. And if n is a number of elements, then you need something like 1.44 bits per element. That's again a lower bound, and we will see algorithms achieving this also as an upper bound with very small errors. One remark. If you have questions, speak up immediately. I think there is a little bit time for this, but if there are more complicated questions, I may say, oh, please defer that for later. Yes. So we have different variants of hash tables. And actually, they are quite interconnected. You can use one variant for implementing the others in many different ways. And what's also very interesting, we will see a number of techniques to implement these variants that are also very versatile and are used in many of these things. So in other words, if I tell you now a lot of stuff about perfect hashing, that will actually give you also many insights on the other specialized hash tables. And the bit vectors are kind of separate. They are not a hash table, but they are actually also used for implementing some parts of these data structures. So are there questions up to this point? So then maybe the main deep dive in my presentation will be on perfect hashing. Let's see. Sorry. Yes. So what's perfect hashing? If you have a set of elements like here, these symbols, we want to map them to numbers from 1 to n, where n is the number of elements. Or that's actually the case if you talk a minimal perfect hash function, MPHF. So we have a set S1 to Sn of elements, injectively maps them to 1 to m. And if m equals n, we have a minimal perfect hash function. There's also generalization that's less well known, that we say there can be collisions, but at most k. So at most k elements may be mapped to the same number. So for this case of minimal one perfect hashing, there's an information theoretical lower bound of something like n log base 2 of e bits, which is about 1.44 n bits. And the interesting question, can we achieve that using practical algorithms? So assuming we can, there are multiple applications of this. There's a recent survey paper with 170 references, and that was with a page limitation, so you could easily find much more. So suppose you have this perfect hash function, you map a key to say an array entry, and then you could store different things in this array entry and get different static data structures. So if you store key and value in this array, you have a static hash table. If you just store the value, you have static function retrieval. Actually, more powerful than other solutions. It's updatable. You can update the associated information. If you just store a random fingerprint, you get an AMQ filter. And what's interesting, all these things are almost space optimal. In each case, the overhead per element is just the overhead of this perfect hash function, which is, I told you 1.44 bits at least, but there are practical solutions nearly achieving that, and even the fastest ones need less than 2 bits. So it's something like between 1.44 and 2 bits. More concrete application example that I have seen in column store databases is where you do a dictionary encoding of your attributes. So in the table, you actually only store the numbers. And then if you somewhere have the inverse of this, you can reconstruct the input, but then you also need this perfect hash function to map your actual keys to these numbers. Right, so let's look at our design pattern. I said we do something completely idiotic and then make it practical. So there's a very nice algorithm achieving the lower bound. Very simple. You just look at the... Yes, question?
Yes. The accepted error probability in the is member query of an AMQ Bloom filter really is for false positives only, so excluding false negatives, right?
Right. I mean, the AMQs I'm talking about have a false negative probability of 0. So you are only allowed false positives. Does that answer the question?
Yes.
Okay, great. So yeah, we had perfect hashing, and I said we look at a sequence of random hash functions, H1, H2, and so on. So we try our first hash function, and we see, oops, there are several collisions between elements. Like here this ghost and the king are colliding, they both result in the value 1, so I cannot use that function. Let's try another one, the second one also fails. I keep going, and maybe the 9th try I make happens to be a perfect hash function. Then, oh, great, I simply store this index 9, and then if anybody wants to evaluate the hash function, it just has to evaluate h9, right? So that has a very low probability of working, meaning it's very slow in construction. But it turns out the probability that I'm successful is the ratio between the number of bijective functions and the total number of functions, n factorial over n to the n, which is about e to the minus n. The space for this, if you want to store this number in a compressed variable bit length encoding thing, is something like the logarithm of this, which is about 1.44n. So it's great regarding space. It's almost optimal space up to a constant additive value. But of course, we have exponential construction time. And also query time for large n will not be good because you have this huge integer you have to read in each step. But I mean, as an algorithm engineer, we already see, oh, well, but maybe we can use this as a base case for small inputs. And that's what we will see in several of the subsequent solutions in one form or the other, some kind of brute force search. Another smaller issue here is you need some variable bit length encoding of this index, which will be a performance and space problem in multiple places, particularly of many small instances you have to solve. So let's go look a little bit deeper into this approach, right? We could use a technique called sharding or sometimes also bucketing, binning, and so on, where we say, oh, we have an additional transformation with a partitioning hash function HB that maps elements of our set to the range n1 to n over lambda rounded down, right? So lambda is our expected bucket size. So we will get a Poisson distribution basically of the bucket sizes. And the expected value will be lambda. And then for each of these buckets, we apply this brute force construction. And in addition, we have some compressed representation of the prefix sum of the bucket occupancies. And if we add this as an offset, then the solutions for the individual buckets can be combined to an overall perfect hash function, right? Right, and the space overhead for this is something like log lambda over lambda for storing the prefix sums. Also there you need a compressed way to represent it, by the way, using bit vectors underneath. Construction time will be linear. That's good news in n, but exponential in lambda with a fairly large exponent. And it turns out you can do that, but you don't want to, right? So that will be very slow. And even the query will not be super fast because you have to decode this compressed prefix sum. And you have a variable bit length encoding for your seed for each of the buckets. And doing these two things is much slower than the fastest perfect hash functions. Okay, but it's the first step. And for theorists, already interesting because you see by seeing lambda as a large constant, you can approach the space lower bound arbitrarily. And it's also actually constant query time. But let's go that one step further because it's a technique that we will also need. So let's say we don't do this random partitioning, but we spend a little bit more effort in the partitioning hash function and use it as a k-perfect hash function. Now all our buckets have exactly the same size, and we don't have to store the prefix sums anymore. So basically, the space we save for the prefix sums, we can invest in representing this k-perfect hash function. And that actually turns out to work out reasonably well. Interestingly, that has been ignored mostly in the past. Only last year, we had a paper on k-perfect hashing where it turned out that you can do that reasonably well. And that greatly simplifies the techniques I will present below. So now we are basically collecting techniques and then putting them together in different ways right now. So another thing that is also brute force, but not exponential in time, is that you get less ambitious. You don't want to guess a perfect hash function immediately, but you do something simpler. You want to guess a function that splits your input in equal halves, assuming it's an even number, say. So here in this example, we have our 8 symbols, and we are looking for a seed that splits the input into 2 sizes of sets of size 1, half of this, 4 in this case. And then recursively, we could split the 4-element sets in 2-element sets, and even the 2-element sets into 1-element sets. And then we have kind of a hierarchical decomposition of our set that leads to a perfect hash function if we go through all of these levels. Yeah, and here probability theory basically tells you you need order square root n trials, and to store the seed, it's log n over 2 bits. And now the really interesting observation for me is that Esposito, Graf, and Vigna in 2020, they observed that these log n over 2 bits are kind of not wasted because the space you invest to store this seed bit here is saved for the smaller inputs, because the lower bound for perfect hashing only applies for n towards infinity, and the smaller sets get easier and easier. And that fits exactly up to an overhead of 1 bit per split. And so they used this as a basis for constructing a highly space-efficient function. So they used this random partitioning thing. And then depending on the bucket sizes, you have some splitting trees that you have to combine cleverly, so that at the end, at the leaves, you always have leaves of size L, up to 1 garbage leaf that you have to treat specially. And then basically what you get is a construction time of n times e to the L, so 2.7 something to the L, which is better than this 578 we had for the simple flat thing. And the additional thing is your random splitting function can give you rather large buckets, and then you have this division thing, and only at the leaves you do really brute force, right? On the downside, the query time goes up because you also have to traverse the splitting tree during query time, and you decode variable bit length encoded data all the time. Overall, it's complicated because of the different tree shapes and these not perfect leaves and so on. But anyway, it's kind of a tour de force, but they achieved very good results. And that's actually the point where we started to join the frackers here. We said, okay, let's do performance engineering on this. And so it's also a good example for fast code, of course. So what can we do here? Of course, we can do parallelization. It's really easy, right? Because the buckets are independent after you've assigned elements to buckets. Our CPU implementation also parallelizes over SIMD lanes, where different lanes try different hash functions. And we can even do bit parallelism by splitting this into 2 parts and then do bitwise rotation to fit things together. And it turns out it also works nice on GPUs, where we parallelize in an even more fine-grained way by the individual, not by over the buckets, but by the individual splitting tasks. You have to solve, grouping similar tasks together so that they can be treated in a single kernel of the GPU. And so that's a nice way to spend the processing powers of GPU to try to do a lot of brute force search here. So looking at numbers, that's quite interesting what came out of this. So let's look at the sequential CPU thing first. So the left plot. And you see here a trade-off between space per key. 1.44 is the lower bound, so you want to be somewhere here near 1.5. Previous techniques were quite separated from this. And the original RegSplit implementation was the first one approaching this. But you see that the construction throughput was kind of limited, but actually not that far. I mean, if you want to be very space efficient, it's super slow. But if you relax your space, and here we are in this pattern, right? If you relax your space a little bit, you are just a factor of 2 slower than the best other methods, right? And it turned out if you really performance engineer this thing, you actually blow the other techniques out of the water, in particular with CPU parallelization. I mean, this is a comparison with this PTH-HEM is actually also parallel, and we are like 4 times faster, although we look at a method that seemingly is outrageously slow. But if you relax space, you suddenly get something which is the fastest, which is quite interesting. It was also disappointed because this green curve is something that we did before, and we were also blown out of the water. And I mean, it was still reasonable because that had a better trade-off for query time, but that's also gone now. So, but you see, performance engineering can make a difference, and this approach of first making something in principle space efficient and then relaxing seems to work extremely well. So actually, we went on. I mean, I said constructing a leaf of size L takes time 2.7 to the L with basic RegSplit, and we developed a succession of methods that has lower and lower exponent here, 1.165, for example, and also reducing the space overhead per leaf. And we were beating the state of the art again and again. We were very happy, but kind of we were also hitting a roadblock here, right? It's still exponential in the leaf size. And we still have this constant number of bits overhead per split. If you see at this, so the black curve is the engineered RegSplit curve we saw before, which is still fastest for the relaxed space, but then these advanced methods were reducing the overhead, but only in ranges of construction throughput that may be not so interesting for most applications. So, and really getting to this low overhead is extremely expensive. So it seems like there was still a gap between theory and practice. But let's go on. I mean, what we then discovered was a quite interesting general technique where we say, okay, looking at this more abstractly, we are finding now a lot of seeds that we have to store in variable bit length encoding. And for each seed, we have a constant overhead. So let's look at this more abstractly. I mean, we have a sequence of capital K random construction tasks, each with a certain success probability P, right? And then the classical way to do this, you do it K times the expected number of trials is 1 over P. So this is the overall number of trials we have to make. The space to reconstruct this is K log 1 over P plus an order K overhead, and that was too much. We could also do the brute force thing, finding a single seed that works for all the tasks, right? But then the number of trials is 1 over P raised to the K, which is exponentially expensive and prohibitive. But the nice thing is then it's plus order 1 overhead. And so the new thing now is that we say, oh, we have individual seeds, but we're storing them in an overlapping fashion. So say the red seed, we store it full. The blue seed, we only store a few additional bits, and the rest of the bits we take from the red seed. And the magenta seed takes a few additional bits, but also some bits from the blue and red seed, and so on. And it turned out if you do it that way, you can, on the one hand, use fixed size seeds, and you don't have these space overheads. What we can show in a very abstract general way is that the number of trials is now k over p times 1 over epsilon, and the space is k log 1 over p times 1 plus epsilon. So for small epsilon, we can get arbitrarily close to the lower bound with kind of polynomial overhead. Now, applying this to perfect hashing, this means we are first doing a 2 to the c perfect hashing at the top, producing many subproblems of size 2 to the c, more or less for free, or with low overhead. And then for each of these subproblems, we use splitting. And on each of these levels, we have a sequence of splitting tasks, right? Where we actually go horizontally over all these subproblems. And we can use the consensus techniques to basically encode these seeds in a very space-efficient way with only linear overhead, linear and 1 over epsilon, right? So overall, what we get is space 1 plus epsilon times 1.44 n, and construction time order over n over epsilon, which got the best paper award at last year's ESA. And if you look at the performance, the curves I showed you previously are here with the overhead, and you see this exponential drop-off in performance when you go to low overheads, whereas the consensus reg split thing goes all the way to almost zero overhead. So in this regime, it's actually that you have 2 to the c perfect hashing for 2 to the c is in several thousand, and then the k perfect hashing is what gives you the overheads, which is quite interesting. But from a point of view of algorithm engineering, we are not completely finished here because we kind of neglected query time. So in this plot now, let's look at space for the elements over query time. So this consensus reg split thing I was so proud of is here with very low construction throughput. Sorry. And all these reg split things are also fairly slow. Then in contrast, if you look at this cloud of points, these are methods that need more space, the most space efficient one around 2 bits, and have an order of magnitude better query time. So the point of view that you can now take is say, oh, let's look at those and start engineering them, so that you get faster queries. And actually this PTR hash thing by Ragnar Groth-Köppern, who is now a postdoc actually in my group, and the fast method, which I did together with Piotr Behling from Lodge, show that we can get, compared to those, another factor of 3 in performance. And I want to outline quickly how to achieve that. So they are all a family of perfect hash functions that can be called bucket placement perfect hash functions. So basically what you do is you take your key and you have one high quality hash function H, which produces what you could call a master hash code. And then you have 2 simpler functions. One converting your hash code to an index into an array of seeds. So you access a seed and use that as an additional input to a placement function. So you take the master hash code plus the seed, and that gives you your perfect hash function value. That's what this formula here tells you. So the intriguing thing about this is that it is very fast from the memory point of view because you have a single memory access to the seed arrays. You have one hash function evaluation and 2 simple functions to evaluate. So, and that's the reason why these bucket placement perfect hash functions are the fastest known ones, basically. So let's look at construction a little bit. So basically what you do is you first assign your keys to the buckets. You have an array of values which are additionally all unoccupied. Now you iterate over the buckets by decreasing size of the buckets. For each bucket, you try seeds from 0 increasing. And for the buckets, you do something brute force. But now you are mapping globally to the number of values. So you check whether your seed works, meaning that all the values are not unused so far. And there are also no collisions between elements in the same bucket. And if that succeeds, you remember the seed, store it in the seed array, block all the values you just used up, and finish your loop. You do that until you have placed all the elements. So that's simple. But it's also not.
There's a question.
Yes?
Question on the master hash code. It looks like that has to be collision free, but we can compute more bits than log n. Is that correct?
Yes, thank you for that question. Perfect, right. So that's actually what I have on the next slide. For this to work, this master hash code must be collision free. That's what you just observed. So for large inputs, what we currently see is that people use 128-bit hash functions, which is not quite as cheap as one might wish, right? And yeah, if there are collisions, you can also retry, but for this to be robust, currently they use 128-bit hash functions, most implementations. Another thing is that during this construction process, the value array fills up more and more. So the success probability for your seeds gets lower and lower, construction gets slower and slower. And actually the number of bits you need for the seeds increases and increases, making things very complicated. So the best bucket placement things therefore use a nonlinear bucket assignment function that kind of equalizes this thing. So you start with large buckets and make them smaller and smaller in expectation, so that all buckets are about the same difficulty. But that makes the query slower by this nonlinear function thing, right? You also have to do variable bit length encoding of your seeds. And this placement function is global, which means that during construction, you have very poor cache locality. So construction is also not super fast. There are tricks to mitigate this, but they are not very perfect, right? And also, if you want to parallelize a construction, you have to shard it into many sub-pieces, which introduces additional overheads. So although it looks intriguingly simple, bucket placement is not perfect. And so what Piotr Behling and me did was to further streamline this to what we call fast, perfect hashing made fast. In actually this year's Alinex, we presented it. So now we allow collisions and use just 64-bit hash functions. And then you noticed correctly that this might mean that there are collisions showing up that we cannot resolve for some buckets, say self-collisions and so on. But what we do is we store these seeds. They are actually fixed width. I will later explain why that works. And if the seed is 0, we say, oh, this failed. We are bumping this bucket to a next layer of the data structure. And that opens up a number of things. It not only allows us to use simpler hash functions, it also allows us to use these fixed width seed things. We also use a linear bucket placement function, bucket assignment function, just multiplicative thing. And in order to make this work, we have an additional factor, like a linear displacement based on the hash function value that maps our bucket to a window in this value array. And that if you go from left to right, that basically means we are moving a window over the value array, and that makes the success probability the same all the time without needing a nonlinear bucket assignment function. And this window can be fairly small so that the construction process is also cache efficient. And finally, the fast plus variant of this simply adds the seed value to the start of the wind, to the value we get here. And then we can use bit parallelism for construction so that the brute force thing almost disappears. It's almost as fast as integer sorting, this construction process. Right, so this bumping process allows us few hash bits, fixed width seeds, and it turns out it can also be used to make the parallelization transparent to the query. So we can just cut this into pieces and bump a few buckets so that the pieces do not interact during construction. Yes, so that was this. And now let's look at an overview slide from the survey paper. So this shows the space overhead on a logarithmic scale and the construction throughput also on a logarithmic scale. And this map shows colors for the fastest method for each of these space construction throughput trade-off, right? So the consensus reg split thing, which is so super space efficient, takes up this left part. The fast variants take up this right part, pretty big block, right? There are few methods that take a little bit more space and are slightly more, achieve slightly higher throughput, but it's actually only like 30–40% faster than fast. And then in this trade-off, there's a middle ground, which is still taken by these brute force things like reg split here and the more advanced variants of reg split, in particular, this morphic reg split that Stefan Herrmann in my group has also designed. Similar plot here where the query throughput, where you see that the query throughput of fast is outperforming all the other things. In particular, this consensus reg split takes about an order of magnitude larger query time. Yes. So are there any questions about perfect hashing here? That was my main deep dive, and I don't have a lot of time for the rest. Questions so far? Okay, so to summarize, there's a little bit of future work here.
Peter, there was a question.
Yes?
What about space performance during construction?
Okay. You mean the space consumption during construction?
Jan Willem, do you want to unmute and ask directly?
No, that's exactly correct. Yes, space overhead during construction.
Yeah, okay. So the way we implemented it is all internal memory, and you have to we store our elements in memory. But in each way, you can have an external memory algorithm that basically stores the keys externally, and basically sorts the elements by bucket, and then you construct by bucket. Or in fast, you have this moving window, so you can construct it in an external memory algorithm would do all these things basically with less working memory than the output perfect hash function. But it's not implemented this way in the benchmarks. Does that answer the question? So it is basically integer sorting what we are doing, and you can do it with an external memory algorithm with basically reading and writing everything twice. Does that answer the question?
Yes, thank you.
Okay. More questions? Right. I mean, what we would like to do is understand this fast method better, and on the other hand, use the consensus technique maybe in faster variants. We've also seen that K-perfect is interesting as a subroutine or by itself. And there the theory is also not completely finished. We are working on that right now. And of course, looking at the applications more closely. Particularly with PTH, we now have such a fast method that applications like in static hash tables could be reconsidered, or also for retrieval and so on. Okay, so the next thing was actually static function retrieval. I will go over that super fast, maybe just the interface. So you can think of this, you have a two-column table with keys and values. And the surprising thing is you don't really have to store the keys. So in this example, if you have a mapping of movie titles to star ratings, you could store this extremely compactly by only storing the stars. So if you have R bit output, you would like to use R in bits. And the interesting thing, you can almost do that. So now I go to fast mode here. The brute force thing is doing this as a linear algebra problem with a random n times n matrix, which is prohibitively slow. Then the first step is you make it sparse. Then you made it banded and sparse. The next step is that you make this band very shallow. And then actually you make it even more shallow, more narrow, so that the solution, the linear equation system cannot be solved anymore. But you again use this bumping technique to throw out a couple of rows. And it turns out you can do that extremely space efficiently with only 1 to 2 bits of metadata for every width of the block here squared divided by log W, which allows you extremely space efficient variants. Let's look at an application for approximate membership query filters, where you basically store as an associated value a random fingerprint. And if you look at the space overhead on the x-axis and the false positive probability you are willing to accept on the y-axis, what you basically see is everything that's green here is this ribbon techniques that I have outlined here. The traditional Bloom filters are in a very patchy way for large F and very high allowed space overhead. They are block Bloom filters, which are more cache efficient, which play a significant role here, but you have something like 50% space overhead. And there are several other techniques that compete around this area, which actually would include perfect hashing, which we haven't benchmarked yet. So for large F, well, for very small F, you can, and some allowed space overheads, and there's a large multitude of methods. But otherwise, this ribbon is dominating everything, and it makes sense to talk about things like 0.1% space overhead without actually a big performance overhead. So this plot here, you have Bloom filters at this point of performance. Block Bloom filters are here, and this bumped ribbon retrieval is just a little bit slower than the general Bloom thing, but can go to something like, say, 0.5% space overhead without starting to deteriorate considerably regarding space overhead. So that opens up also new applications of retrieval data structures. Yeah, similar thing for bit vectors. So you have a vector of bits, and for many compressed data structures, you need the two operations rank. You count ones up to a given position and select where you find the position of a given k-th rank. And there was a gap between theory and practice. The bottom line now is that if you look at these triangles and difficult inputs, we have something with something like 1% of space overhead, which is much less than previous practical solutions. And it's actually also much faster. So we are kind of dominating them for the difficult things. For random easy inputs, yeah, those with high space overhead are a little bit faster, but actually that's all in a very narrow range. They are basically doing, on average, they are all doing the same thing. So that's probably all I want to do here. let's wrap up with my final slide. Thank you very much. Are there additional questions?
Questions, anybody? We have time for wrap-up questions. There's applause ringing in the room. Questions, anybody?
Just a reaction to the hash function. The GX hash was a little bit surprised to see that used. It is not necessarily the fastest. Do we really care about quality that much, or why not use, for example, XX hash?
Good question. We could try that. Yeah, so GX hash uses cryptographic primitives, but I can say it's not really a bottleneck because cache faults and so on are more important. But I would guess that you can also try faster hash functions.
Yeah.
So you can try that.
Any other questions? Here's a question. I don't work in this very subject, but your results look fantastic. Still, have you tried or do you plan to further explore optimization potential using AI?
Yes, certainly. That's a candidate for this. There are repositories of implementations, and you can say, oh, please use algorithm engineering to optimize hyperparameters, or here's an idea how to use consensus in a bucket placement. Can you implement something for me? That's something one could try, yes.
Here's another question.
Rec split. So for basic rec split, I think it would be like 4 for the very fast things and 10 to 12 for the slow ones. And for the advanced methods, we approach leaf sizes of above 100. Very interesting.
Great questions. Any more questions? We're right at the top of the hour, so we have time for 1 or 2 more questions if anyone wants to ask. I think there's no more questions. So thank you very much, Peter, for the fantastic talk. And
thank you for the invitation.
And we really appreciate everyone coming for the Fast Code seminar. This wraps up today's talk. Next, in May, we have 2 talks. Mosharaf Chowdhury talking about optimizing energy. Laxman Dhulipala will be talking towards the end of the month, topic to be announced. That completes today's talk. Thanks, everybody.
Okay.